Okay, so let's continue our discussion. Let us start by recalling that we have seen these three examples in this section: 561, 562 and 563, and in each one of them we investigated this group and its fixed field. Now it turns out that in the first and third example, the fixed field of this group in each one of them is equal to f itself. Of course, f is a subfield of the fixed field of this. That is by the definition of this group. However, that is not always equal to just f itself. It may be larger than f also, and that one we see in this example. In this example, the fixed field of that group turns out to not be f but k itself, the entirety of k. And this observation prompts the next definition. An extension k of f is called a normal extension of f if k is a finite extension of f, and that is one condition. K needs to be a finite extension of f, and then this should happen. F is the fixed field of this group, the group of automorphisms of K relative to F. That means the extensions K that we saw in these two examples are normal extensions of the F there, of the F's there. But this is not a normal extension. And next we have a result about normal extensions. So let's see that. This is, I think, 4. Yeah. Theorem 564. Oh, and let us also observe one more thing. If K is a normal extension of F, that means the fixed field of this group is F itself, which means in particular that if you consider anything in K which is not in F, then that thing will not be in the fixed field of G, and hence at least one automorphism from this group will change that thing, that field element. That is what I am saying is this: if K is a normal extension of F, then for any element x which is in K but not in F, there exists some sigma in this group such that x sigma is not equal to x. That's because if no such sigma exists, then every sigma in this group fixes x, but then x by definition would belong to the fixed field of this group, which is not possible because the fixed field is F itself. Alright, so let's now see the theorem. Let K be a normal extension of F. all right, and HB a subgroup of the group of automorphisms of K relative to F. We are now going to consider the fixed field of the subgroup H. Let KH be the set of those elements X in K which are fixed by every element in H for all sigma in H. So by definition, this is the fixed field of the subgroup H. Be the fixed field of H. Then what is this theorem saying? Then comes the conclusion. The theorem is going to say two things. One of them is the degree of K over KH. I mean, you can see that KH is the fixed field of H. That means it's after all a field, and moreover it's a subfield of K. So we can of course talk about the degree of K over KH over this subfield, and that degree, this theorem claims, is nothing but the order of H. Then number one, the degree of K over KH is equal to the order of H. That is the first claim. And the second claim is this: the group of automorphisms of K relative to the subfield KH is actually H itself. So we are getting equality here. In general, we have inequality. For any type of extension, finite extension K, we have inequality here. We have already seen that such a degree is greater than or equal to the order of the group. That we have seen for the entire group G, K, F, but that was an inequality. Here, however, we are additionally assuming that K is not just a finite extension but actually a normal extension. Then we are getting equality. Now, if H is a subgroup of this group, what would happen if H is equal to the entire group? Let's see. If we assume that these things are already given to us, then in particular, if H is the entire group of automorphisms of K relative to F, then the degree of K over F is equal to what? Oh, okay. So if H is this itself, then what is the fixed field KH of this group H? Because K is a normal extension, the fixed field by definition of normality is equal to F. That means in this particular case, KH is equal to F. Is equal to the order of H, which means this is equal to the order of the entire group of automorphisms of K relative to H. And well, in this case, what are we getting? Do we have anything else to say here? No. Nothing else, because KH is already F. So from this we are not getting anything new. So this is the thing. This is a particular case of this result. Okay, so let us now see the proof. Now the proof begins by considering this fact. The fact is that if we choose any element x from the fixed field kh and apply any sigma in h on that element, what are we going to get? We are going to get that element back, because that is the definition of kh, right? Note that for any sigma belonging to h, x sigma is equal to x for all x belonging to kh. This is clear because the definition of kh is here in front of us. But what does this mean now? This means that any element sigma in H belongs to this group. This implies sigma belongs to the group of automorphisms of K relative to KH. Why? Because by definition this is the group of those automorphisms of K that fix every element of KH. Sigma is one such automorphism of K which fixes every element of KH. That is why sigma belongs to this. But that means what? Sigma is any element in H that now belongs to this group. Hence, H is a subgroup of this. Alright. Thus, the order of H is less than or equal to the order of this group. But we already know something else about this order from a previous result, and that previous result is Theorem 562. Okay, the one that we saw recently, we proved. By Theorem 562, we also have this inequality. This is less than or equal to the degree of K over KH. So that means this is less than or equal to this, and this is less than or equal to this. Now if we can somehow show that this degree is equal to order of H, then all of these three quantities will be equal, and from that we will get our conclusion. So that will be our aim now, to show that this degree is equal to the order of H. Now how can that be achieved? For that, we are going to use another result from not from this section itself, but from the previous section. You remember that we have already proved that any finite extension of a field of characteristic 0 is a simple extension, and we have already agreed on the fact that we will always use fields of characteristic 0 here in this chapter or the rest of this chapter. So all our fields are of characteristic 0. That means any finite extension is going to be a simple extension. In particular, K is a finite extension of KH. So K will also be a simple extension of KH, which means that you should be able to get K by adjoining a single element to KH from K. And that is the result theorem 551. Yes. By theorem 551, K is equal to KHA for some A belonging to K. In general, we know that a finite extension can be obtained by adjoining finitely many elements, but for simple extensions, one element is enough, and that is the case here. For some single A in K, if you adjoin A to KH, then you get the entire K. Alright. Now, what does this mean? If we go back to the original first section from field theory, when you have something like this, what does it mean? It means that A is algebraic. The element A in K is algebraic over the base. Of course, the base field means this subfield KH, and has degree which is equal to the degree of this extension. Do you get what I am trying to say? Let me again say it. This means that A is an algebraic element over KH of some degree that is equal to the degree of K over KH. And what is this degree? This degree is the degree of the minimal polynomial of A over KH. It is the degree of the smallest degree non-trivial polynomial that A will satisfy, whose coefficients are coming from KH. Okay, this fact we already know, and that's what the author has written here also. Thus, and minimality of that polynomial will make it irreducible. Thus, A satisfies an irreducible polynomial of degree m, which is equal to the degree of K over KH, whose coefficients are coming from KH. That means it's a polynomial over KH, whose coefficients are in KH and satisfies means A satisfies, this element A satisfies no non-trivial polynomial over KH of smaller degree. That means not only is A satisfying such a polynomial over KH whose degree is m, but also no other polynomial which is non-zero and has degree smaller than small m. That makes it the minimal polynomial, and that also makes it irreducible over KH. And this, of course, is coming from Theorem 513 from the very first section. Alright, so let us now write the elements of H out. That is, H is a finite group, so it will have finitely many elements. So we can write like this. Now let H be this group, sigma small h, where sigma 1 is the identity and small h is the order of capital H. And small h is equal to order of capital H. Okay, now what we are going to do, we will now consider elementary symmetric functions on some symbols and some elements, and those elements are going to be this. Now consider the elementary symmetric functions in these things: a sigma 1, a sigma 2, and so on, a sigma h. Because sigma 1 is the identity, it's after all nothing but the identity automorphism. So a sigma 1 is nothing but a1, and you know very well what elementary functions we are talking about. Let us denote the first one by alpha, alpha 1. So alpha 1 is nothing but the sum of these things. A sigma h, that is summation a sigma I, where I varies from 1 to h. Then alpha 2 is again such a sum, but taking two such things at a time, two distinct such a sigma i's. So it is a sigma I, a sigma j, where to indicate the distinctness we impose the condition that I is less than j. But satisfying this condition, all possible I and j have to be taken, and it goes like this. And finally we encounter alpha suffix h, which is the product of all these things, because we end up taking all h of these symbols at a time, and that just gives us one thing, one term, which is the product of all these things. That is also a sum, but in that sum there is only one term, so we do not write summation. Okay. Now next, the author says that all these elementary symmetric functions, these things, these elements are invariant under every sigma coming from capital H. Let us see how that statement is true. But I mean, we put it in within brackets. Okay. Let sigma be any element of H. So this sigma is any one of these sigma i's. What can we say about this? When we apply sigma to alpha 1, what do we get? Using the fact that sigma is an automorphism and this is a sum, you simply get this: a sigma 1 sigma plus A sigma to sigma and so on, and finally A sigma H sigma. I have simply casually written A sigma 1 sigma. Whether you interpret this as the sigma image of A sigma 1 or the sigma 1 sigma image of A, ultimately the meaning is same. So I am not further putting these things within brackets or anything like that. Okay, the meaning is clear. Alright, but now can we say something about this sum? Note one thing, that because these sigma i's are actually forming a group, the group capital H. So sigma 1, sigma, sigma 2, sigma, all these things are again in the group because every group is closed. So this sum again takes this form, A sigma something, some sigma I1. We don't really know what this sigma 1 sigma is, but it is again some sigma. So A sigma I1 plus A sigma I2, like that, A sigma IH. Alright, but that itself won't tell you that this is again equal to alpha 1. Why? You are in fact again getting, you see, this A sigma I1 can be found as a term here itself somewhere, because sigma I1 after all is again one of these functions, one of these automorphisms. But are we really again getting small h number of terms? What if there is a collapse, there has been a collapse? Say A sigma 1, sigma I1 is equal to A sigma I2. What then? Or actually, in a more elementary manner, suppose sigma ij, okay, because I now itself has a suffix of its own, so let me just call it sigma ij. If sigma ij is equal to sigma I sum j prime for I prime not equal to j prime, if this happens, then there has been some sort of collapse. So in this sum, although we are seeing h number of terms, but they may not be distinct. Or I mean, what I'm trying to say by that is that you won't get all of these things, but you get something repeated. But then, by the notation we are using, what is sigma ij? Sigma ij is sigma j sigma, right? You can see here we are calling sigma 1 sigma, sigma I1, sigma 2 sigma, sigma I2, and so on. So sigma ij is sigma j sigma. Similarly, this one is sigma j prime sigma. But then by the right cancellation law in the group capital H, we have this. Sigma j is equal to sigma j prime. This, however, is a problem because we have considered all these sigma i's to be distinct elements in capital H. So if I prime and j prime are distinct suffix values, how can these two elements be equal? They cannot be. So this is a contradiction, and that is why no such collapse can occur. And our supposition is wrong, which means that this sum again is equal to this sum itself with the order of the terms changed in some way. Okay, so that is why we can again write this, keeping in mind that by this we do not mean that this is equal to this is equal to this. That may not be true, but after all, the sum is just the previous sum. and this is nothing but alpha 1. And that's how we are getting the fact that alpha 1 sigma is equal to alpha 1. And by following similar argument, you will be able to show that alpha 2 sigma is also equal to alpha 2, although it looks like that will be rather difficult because here we have a sum where the terms are products, but that is not difficult at all. It is actually, it will follow the same pattern. That argument will also follow the same pattern. So that part I am not doing, and anyway the author has asked us to do it ourselves, and so that means we are now going to claim that all these alpha i's are invariant under every sigma coming from capital H. And in particular, you can see that the same argument, actually almost exactly the same argument you can use in this case, where in place of sum you have just product, that's it. So let me just end this little discussion here itself, and let me just write what the author has written. All the alpha i's are invariant. Invariant means they do not change under every sigma coming from H. But note that because the sigma i's are what after all? They are automorphisms of K. And what is A? A is an element of K. So all these things now, all these A sigma i's are also elements of K, and that makes all the alpha i's also elements of K. And they are all fixed by everything coming from H. So by the definition of the fixed field for H, capital H, all these alpha i's belong to the fixed field K suffix H. Hence, belong to the fixed field of H, capital H, which is KH. Now, these alpha i's are the roots of the following polynomial over KH, and that polynomial is this: Px equal to x minus a sigma 1. Well, hold on, am I writing the correct thing? No, these alpha i's are not the roots. The a sigmas are the roots. Yes, this is wrong. What I have written here is wrong. The alpha i's are not the roots, they are going to be coefficients. Instead, I should have written this. Yeah, it immediately looked wrong. Now, A. Actually, our focus is on the element A itself, as well as, but the others also are A sigma 2. This A is of course A sigma 1. Is a root. Others are also roots, but this is also a root. That's what we need right now, of the following polynomial over kh, and that polynomial is this x minus a sigma. We do not write a. If you want you can write a, but let's just show the pattern fully. This is a sigma 1, this is the next one has a sigma 2, and like that the final factor has a sigma h. So clearly the form of this polynomial shows that these are its roots. But if one multiplies the terms out, collect the coefficients and write the polynomial in the form of a polynomial, then by the definition of symmetric elementary symmetric functions, this will be what? There are h factors, so this will be x to the power h minus the sum of all these a sigma i's, that is alpha 1 x to the power h minus 1 plus the sum of products of this a sigma i's taking 2 at a time, which is alpha 2 x to the power h minus 2 minus and so on. In fact, such a product of linear factors is the source of elementary symmetric functions. We have already said this before. You may have a little confusion here, but I am coming to that later. Okay, let me just complete this first. And so on plus minus 1 to the power h times the product of all the a sigma i's, which is alpha h. The confusion I was mentioning just now is that you have come across elementary symmetric functions of indeterminates x1, x2, x3 and so on. But these are not indeterminates, these are actual field elements. The word here, elementary symmetric function, may confuse you in that sense, but we are just using the form of these elements alpha 1, alpha 2, and we are simply calling them elementary symmetric functions because they have the form of elementary symmetric functions. Okay, so that's just it. What we call them is not the problem here, but what they are ultimately going to give us, that is what matters. Alright, so we now have this. Okay, now some remarks about this last line we have written. What have we written? A is a root of this polynomial over kh. Why is this a polynomial over kh? That's because its coefficients alpha 1, alpha 2, 1 of course is there. All these coefficients are elements in kh, and that's where we are using this conclusion. See, here we have seen all the alpha i's belong to kh. So this is a polynomial over kh. Is it a non-trivial polynomial? Yes, it is, because this coefficient, we don't really know what the alpha i's are. That is, whether they are 0 or not, we don't know. But we at least know that this leading coefficient 1 is non-zero. So it is a non-trivial polynomial. That small a is satisfying, and at the same time, it also is a polynomial over kh. So what can we now say? You see, we already know this. Huh? We already know this, and we also know something else. We know that A is algebraic over kh of degree what? Degree m, which is the degree of the smallest non-trivial polynomial over kh that small a will satisfy. That is the smallest, and that polynomial must have degree n. This is another polynomial which may or may not be the smallest, and it has degree h. So h has to be greater than or equal to small m. Okay, small m is minimal, h is something. Hence, h is greater than or equal to small m. However, what is h? H is nothing but the order of f. I should have written it more on that side. Let me write directly like this. Order of h equal to small h is greater than or equal to small m. But this small m is what? If you go back to small m, you will see that this is nothing but the degree of k over f. K, no, not f, kh. Kh, sorry. It's not f, it's kh. Alright. But we already have something else. We already have proved something else before doing all these things, and that thing is simply this. Order of h is less than or equal to the order of the group of automorphisms of k relative to kh, which is less than or equal to this degree. That is, this is greater than or equal to this, but at the same time this is also less than or equal to this. That means they must be equal, and this thing trapped in between them also is forced to be equal to them. Hence, order of h is equal to order of this is equal to this degree, and that gives us everything. I mean, the first conclusion we have here directly. And what is the second conclusion? Because we already know that h is a subgroup of this group, and at the same time it has the same order as this group, so it must be equal to the group. This implies, and that is the second conclusion, that h is equal to the group of automorphisms of k relative to kh. This completes the proof. And that particular case we have already seen. If h becomes equal to that original group g, k, f, then the degree is satisfied. I mean, that degree and group order relation, that becomes an equality. The number of elements in the group of automorphisms of k relative to f, okay, in that case, if h is equal to the entire group, is equal to the degree of k over f. So here we have actually improved that result, which tells us that in general we have this inequality. But if k is a normal extension of f, then this becomes an equality. Okay, that's what we conclude from this. Now, after this, the story, of course, it goes on, but today we stop here itself. The next field theory video will come this Sunday itself, because we have already completed one section in analysis. So for that section I have to solve exercises. So that can be done, but this also can be simultaneously done. So this Sunday again we are going back to field theory. But that's just it for today. So see you in the next upload when that comes out. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.